In this video, we'll determine where the power series f of x given by the following expression converges or diverges. Let's write out a few of the terms. When I do so, the first term will be 1 over 3. I'm taking n to be 0, so this will be 3 to the 0. This will be x to the 0, and this will be minus 1 to the 0, and all those factors will be 1. And then I'll have 0 plus 3, so I'll have a factor of 3 in the denominator, so 1/3. Each successive term will have a power of x appearing in it, and then we'll see a power of 3 increasing, and then in the denominator we'll also see n plus 3, which when n is equal to 0 gives you 3, but as I increase n here, I'll see this factor go up by 1, so we'll see 4, 5, and 6. I want to determine where this series converges, and at least for one value it's obvious that this should converge at x equal to 0. This is a power series which is centered at x equal to 0, and if I plug in 0 into my function, if I plug it into my series for x, f of 0 will wipe out all the terms after the constant term and we'll be left with a 1/3 only. So it will converge at x equal to 0 to the value of 1/3. What we want to determine is if there are other values of x for which it converges. To do so, we're going to use the ratio test, and I'm first going to identify the nth term of the series. I'll call it an, and this is the nth term of our series. The next term of the series we get by evaluating n at the next value, so everywhere I see an n, I replace it with n plus 1. So we'll see the exponents go up 1, and then it was n plus 3 over here, so when I evaluate at n plus 1, I'll have n plus 4 now. The ratio test says I should look at their ratio of those consecutive terms. Some of those terms may be negative for different values of x, so we should take absolute value of the ratio, and we're in fact going to be testing for absolute convergence here, so I'm going to put things in absolute value. And then I'm going to take the nth plus 1 term in blue and multiply it by the reciprocal of the nth term. So I'm going to take the reciprocal of that nth term and multiply it there, and I've copied that over, and multiply these two expressions in absolute value and see what happens as n becomes large. Obviously there are some factors that are similar in nature. There's 3 to the n over 3n plus 1, so we'll keep those together. There's the n plus 3 and the n plus 4. We'll keep those together. All of those are positive numbers. N is going from 0 to infinity, so it's at least positive or at least non-negative, and so I don't need absolute values around any of this part of the expression. The negative signs here in the alternating parts of the terms will be ignored because we're taking absolute values, so I don't need those. But of course my x value could be negative, in which case I should preserve the absolute value around that ratio. I'll have x to the n plus 1 over x to the n. I'm going to do some canceling that appears here. I'll have 3 in the denominator. I'll have this n plus 3 over n plus 4, no change there. And the reason why we like the ratio test here is that we'll see all these powers of x cancel, and I'll be left with just the magnitude of x in the expression. I now let n go to infinity. This is constant. This factor here is linear over a linear. This will be same degree, so as n becomes large, this will go to 1. And then whatever the value of x is will still appear in the answer as I take the limit here, so I'll have 1/3 times the magnitude, the absolute value of x, as n becomes large, as n goes to infinity. The ratio test now tells me that this will converge absolutely provided the limit that I got is less than 1. So in other words, when 1/3 times the absolute value of x is less than 1. Another way of saying that, by multiplying both sides by 3, is that magnitude, or the absolute value of x, should be less than 3. The ratio test tells me it diverges when that limit is greater than 1. In other words, when the absolute value of x is greater than 3. And it's inconclusive at the endpoints, when 1/3 times the absolute value of x is equal to 1. We don't really know what happens by the ratio test here. And so when the magnitude of x, the absolute value of x, is 3, we really don't know whether or not it converges or diverges. We should think about this as an interval. What's happening here is at the center x equal to 0, it's converging. We can move as far away as 3 units from 0 and it will converge absolutely. But outside that interval, when my magnitude of x is bigger than 3, it will diverge. So either here or here it will diverge as well. In particular, the radius of convergence is what I call capital R, is 3, because I can move at most 3 units away from the center and it will still converge. We can address what happens at these endpoints at -3 and 3 individually. The ratio test was inconclusive there, and we can consider those as individual series now. I'm going to take f of 3. That means where I see x to the n, I'm going to plug in 3 and I'll have 3 to the n. Those will cancel with the 3 to the n in the denominator, and I'll be left with the following series. This is an alternating series. The terms are going to 0 and decreasing, and therefore will converge by the alternating series test. I can consider what happens at x equal to -3 by evaluating in a similar fashion at -3 now. The powers of -3 the powers of 3 to the n will cancel just as before, but now I've got an extra minus sign. It's -1 to the n, and there's a -1 to the n here as well. If those powers are positive or both negative, they will cancel each other out, and the series I'm really looking at in the end will be 1 over n to the 3, or n plus 3. Notice that this is effectively a harmonic series. It's not alternating anymore and will diverge. You can prove that that diverges by using the integral test. If you were integrating 1 over x plus 3 from 0 to infinity, you'll see that this integral diverges. And so in conclusion, we can see that it diverges at -3, converges at +3, and so the interval of convergence is -3 to 3, including +3 but excluding -3.